Alright, so in this video, we're going to talk about compound angles. So we're going to be making use of basically three concepts, but let's revise a few concepts like SOHCAHTOA. Now, if you have a right angle triangle and you have a right angle triangle and you have a reference angle, let's say theta. So stands for sine theta equal to opposite over hypotenuse. Car stands for cos theta equal to adjacent over hypotenuse, and TOA stands for tan theta equal to opposite over adjacent. Now this is basically what three of them stands for. Now how do you identify which side is the opposite and which side is the adjacent and which side is the hypotenuse? So this is a right angle triangle. This is the 90-degree symbol. Now the longest side, as this side that is slanted, is the hypotenuse. Now the placement of the opposite and the adjacent largely depends on the reference angle. So let's assume the reference angle is here. The side the reference angle is facing is called the opposite. Then the side where the reference angle as well as the 90 degrees resting on is the adjacent. So if we are to draw the reference angle in another place, let's say here, this is the place, this is the line that both angles are resting on. So this is the adjacent, and this place is where the angle is facing. So this is the opposite. So regardless of the orientation of the triangle, it still stands. So even if the triangle is drawn this way, it's still the same. Even though it's this way, it's still the same. This still remains your hypotenuse, this still remains your adjacent, and this remains your opposite. So we're going to be taking a few questions on this. Okay, before we go to that, aside the fact that you can apply SOHCAHTOA in tackling this kind of question, okay, now aside from the fact that we made mention of SOHCAHTOA, this is your hypotenuse, this is your opposite, and this is your adjacent, right? Now, Pythagoras, a man named Pythagoras, came about to say that the three sides of a right angle triangles are interrelated. So he said that when you square the hypotenuse, it gives you the opposites all squared plus the adjacent all squared. So this is what a man called Pythagoras said about a right angle triangle. So we're going to be applying these two principles, SOHCAHTOA, to solve. Now for instance, let's say our right angle triangle For instance, let's say our right angle triangle has a hypotenuse of 5, a reference angle theta, and an adjacent of 4. Now, how do you get the opposites? It's simply going to be 5 squared. Let's call the opposite x. 5 squared is equal to x squared plus 4 squared. So in order to get x squared, you have to make it the subject. So 5 squared minus 4 squared equal to x squared. 5 squared gives 25 minus 16, which gives x squared. 25 minus 16 gives 9, which gives x squared. Now if you find the square root of both sides, x gives you 3. So the opposite is 3. Now if we take another example, if let's say the hypotenuse is not given and you're meant to look for the hypotenuse, remember what we said, the hypotenuse squared is equal to the opposite squared plus the adjacent squared. Now the hypotenuse squared will give you 3 squared plus the adjacent, which is 4 squared. Hypotenuse squared gives you 9 plus 16. Hypotenuse squared gives you 9 plus 16 gives 25. Then hypotenuse gives the square root of 25. Hypotenuse is equal to 5. So this is, we've gotten back our hypotenuse. Now let's assume the adjacent was not given and we want to prove whether this principle is correct. Let's say it's not given, let's call it adjacent. So the hypotenuse squared is equal to the opposite squared plus the adjacent squared. Now the hypotenuse is 5. 5 squared is equal to adjacent squared. Okay, sorry. 5 squared is equal to 3 squared plus adjacent squared. 5 squared gives you 25. 3 squared gives you 9 plus a squared. Bring this over to this side. 25 minus 9 gives you a squared. 25 minus 9 gives you 16, which is equal to a squared. Finding the square root of both sides, this will cancel out this. Square root of 16 gives you 4. That means a is automatically 4. So this principle works, you understand? Now, instead of going through this long process, they are pair of numbers that when you see, you know that, okay, if one of them is missing, you know how to compensate for it. Let's give an instance. Just like this example we took now. If you have a right angle triangle with either a right angle triangle having 3 and 4, automatically you know that the other side will be, if you have a triangle having 4 and 5, automatically you know that the other side will be 3. Understand? If you have a triangle with sides 3 and 5, you know that the other side will be 4. So this is called the Pythagoras triple. A Pythagoras triple. Understand? A set of numbers that always go hand in hand. So some examples of Pythagoras triple is like the one we have here: 3, 4, and 5. Now this the first two can be the adjacents or the opposites interchangeably, but the last one indicates the hypotenuse. Obviously the biggest number is the hypotenuse. So another example of a Pythagoras triple is 5, 12, and 13, where 13 stands for the hypotenuse. Another example is 7, 24, 25. Yeah, another example of Pythagoras triple is 11, 60, 61. Another example is 12, 35, 37. And we also have 13, 84, 85. We also have 20, 21, 29, and so on and so forth. Understand? So there are lots of Pythagoras triples, but we'll just take this ones as reference for examples. Now let's take a question. So the question can say that if sine A is equal to 7 over 25, comma, find cos A. So this is what you're going to do, and okay, find cos A and tan A. Now, first things first, you have to apply the knowledge of your SOHCAHTOA or your right angle triangle. So let's draw a right angle triangle. So assume this to be a right angle triangle. The reference angle in this case is A. So this automatically becomes, now this is your opposite. According to SOHCAHTOA, remember that sine theta is equal to opposite over adjacent. That means this reference angle now, theta is equal to A, the opposite is 7, and the adjacent is 25. So the opposite here is going to be 7. The adjacent, sine is opposite over hypotenuse. So the hypotenuse is going to be 25. And we're meant to look for the adjacent. Now, you can either use the Pythagoras formula, or this is a Pythagoras triple, where you have 7, 24, 25. So we already have 25 and 7. So you know that the adjacent should just be 24. So how will this help us? Now, cos, remember cos A will be equal to the adjacent over the hypotenuse. So what is the adjacent? 24 over 25. We've gotten this. Now we'll go for tan. Tan A will be the opposite over the hypotenuse. Now the opposite is 7. Sorry, not hypotenuse. Opposite over adjacent will give you 7. Okay, opposite is 7 over the adjacent, which is 24. So this is a very good example of the application of SOHCAHTOA and Pythagoras triple. So we go to the next. Okay, before we go further, if you see a question like this where the type of angle is not specified, like the reference angle in this case is A, right? Now sometimes they will tell you that A is acute or A is obtuse. Now if the reference angle is not identified or described, just assume that it's acute. Understand? So in this case, we assumed that the reference angle is acute. That's why we solved normally. So we're going to take an example where the reference angle is not acute, it's obtuse. So we know what to do. Now, question 2 says if sine B gives you 20 over 29, you should find cos B and tan B if B is obtuse. So remember, we said acute angles are angles that are less than. So for acute angles, the angles that lie between 0 to 90 degrees, we said obtuse lie between 90 degrees to 180 degrees. So this is basically what acute and obtuse mean. So in case they're not put this way, you know what to do. Now what you're going to do here is that there's something called quadrants. There are 4 quadrants. We have first, second, third, fourth. Now there's a way I map out this. I call it CAST. CAST. What this means is that in the first quadrant, all, this stands for all, In the first quadrant, trick all the tricks, that is sine, cos, tan, and so on, are positive here. For the second quadrant, is only sine that is positive. For the third, only tan is positive, and for the fourth, only cos is positive. So what it means is that if I say something is obtuse, remember I said when you are drawing your angles, you always start from the positive, from this side, positive x. Remember from the video on complex numbers. So we always start from here. We move towards the anti-clockwise direction. Remember we said angles that move in anti-clockwise direction are positive angles. So we're working with positive angles. So always starting from here, you're moving towards this direction, down to this place. So you start from here, you go all the way down to this place. So when you start, obviously acute angles will fall between these two regions. You understand? That means in the acute region, all tricks are positive. You understand? But when you say something is obtuse, it means you've gotten to this second quadrant, because this is now the region between 90 degrees and 180. The angles on a straight line is 180. This is what I mean. I'm moving this way. This is 90 degrees. Then after you pass this line, you have 90 degrees. When you get to this point, you have 180 degrees. That means the angles between 90 degrees and 180 degrees will fall in between this place. You understand? So that's why the question that we're working with is in the second quadrant, meaning that only sine is positive there. So any other thing there will be negative. That's why from the question we can see that sine is positive. If the question gave us cos, first of all, you see that it will carry negative sign. So let's solve this. Remember cast, C-A-S-T. We start from down, C-A-S-T. Now, so we're going to look now. How does this affect our solving? It's not going to affect it that much. The only thing is that you solve all this thing normally like the previous one, but at the end of the day, you just add minus to show that it's in second quadrant. Understand? So let's quickly solve this. So this is a right angle triangle. We have our reference angle B. So now in the ideal sense, I'm going to show you how to actually draw the diagram, but let's just use this for the sake of convention. Now the opposite, remember sine B will be opposite over hypotenuse, right? According to So. Remember So Katwa. Now your opposite is 20, so this automatically is 20. Your hypotenuse is 29. So we're looking for your adjacent. So this is also a Pythagoras triple. So we have 20, 21, 29. Yes. So we have 20, we have 29. So automatically this becomes 21. So we can quickly solve. Now, cos B is equal to adjacent over hypotenuse. What's your adjacent? Your adjacent is 21, your hypotenuse is 29. But for the fact that they said B is obtuse, remember our quadrants, C-A-S-T. So in the second quadrant, only sign is positive. So our answer will be negative 21 over 29. Then we go over to tan. So tan B is equal to opposite over adjacent. Now the opposite is going to be opposite is 20, adjacent is 21. So because it's in the second quadrant, the obtuse quadrant is going to carry a negative sign. So these are the solutions to this question. Now let me show you the conventional way of actually drawing that diagram, since they say B is obtuse, because obviously looking at B here, B is an acute angle because it does not exceed 90 degrees. So this is the actual way of drawing it. It's going to be this way. You're going to indicate the quadrant. So you're going to draw this all out. Then you're going to draw your triangle starting from this point down to this point. And into this point. Yeah. So let's draw it again. Yeah. So now this is basically how the triangle is going to look like. This is obviously going to join this. So now your B will be from this point. B will start from this point. You're going to go this way. So this is your B, your angle B. So this is still going to be 90 degrees. This is still going to remain your opposite, which is 20. Your hypotenuse, which is 29, and your adjacent, which is 21. So this is basically how the diagram is going to look like. An alternative way of solving this is, if the angle is given, you can simply say 180 minus whatever is here to get your acute angle. Then you solve it normally without considering the quadrants. But let's not overcomplicate things. Just stick with this if this is only what you understand. So this is basically the idea between acute and obtuse angle in terms of trigonometry. So we're going to go further to the next section, which is compound angles, just like the topic, compound angles. So what are compound angles? This is just like I'm going to show you. If you have a trig, let's say you have sine, let's see 45 degrees, right? You can express this as sine 15 degrees plus 30 degrees. So when you have a trig with the angles, with two angles being added together inside the trig, this is a compound angle. So there are basic formulas for compound angles. So the first is for sine. Let me quickly clean this, erase this, so we'll continue. So the first trig is sine. So sine A plus B gives us sine A cos B plus cos A sine B. The second one is, if you have a negative sign, sine A minus B is going to give you sine A cos B minus cos A sine B. So these are the first two compound angles. Now the third is when you get to cos. So cos A plus B gives you cos A cos B minus sine A sine B. Please take note of the symbols. It's not an error. For cos, the plus has minus. You understand? The fourth is cos A minus B. This gives you cos A cos B plus sine A sine B. Now the fifth is for tan. So tan A plus B gives you tan A plus tan B over 1 minus tan A tan B. So when we start solving some examples, you understand how this formula works. So the sixth formula is tan A minus B gives you tan A minus tan B over 1 plus tan A tan B. Please take note of the symbols. Don't mess it up. As if you mess it up, all your solving will be wrong. Understand? So we're going to take some examples in reference to this. Or before we take an example, there are special angles. I don't know if you know them. Special angles that how do I put this? Just know that there are special angles. So an example of a special angle is 30 degrees. An example of another one is 45 degrees, and we have 60 degrees and so on. So we're going to be working with these three. Now it's important to note that sine 30 degrees gives you 1 over 2. Sine, okay, not sine no more. Sine 45 degrees gives you root 2 over 2. Sine 60 degrees gives you root 3 over 2. Now for cos 30 degrees gives you root 3 over 2. Cos 45 degrees gives you root 2 over 2. Cos 60 degrees gives you 1 over 2. So these are standards, you understand? They're standards, they don't change. Now for tan 30 degrees gives you root 3 over 3. Tan 45 degrees gives you 1. And tan 60 degrees gives you root 3. So these are the three basic special angles we are going to be working with in the course of our calculations. Application with in unison with compound angles. So let's take some examples. The first example is this. Example, if you're asked to solve this without using a calculator, which is sine 15 degrees, without using a calculator, how do you solve this? Now you can express 15 in terms of special angles. So sine, now you can use 45 and 30. So 45 degrees minus 30 degrees gives you 15. So this is a compound angle. So going back to the formulas for compound angles, the one that has minus. So it said that whenever you have sine A minus B, it's going to be sine A cos B minus cos A sine B. So we're going to apply this now. Trying to apply this here, it means that our A is 45 and our B is 30. So we just plug it into the formula. So the formula says sine A cos B. So sine 45 cos 30. All these are in degrees. Minus cos A sine B cos 45 degrees sine 30 degrees. So this is basically what the compound angles, the formulas help us do. So we know that sine 45 from our special angles is root 2 over 2. Multiplying cos 30 is root 3 over 2. Minus cos 45 is root 2 over 2. Sine 30 is 1 over 2. So solving this, you're going to have, when you multiply this, you're going to have root 6 over 4 minus root 2 over 4. You look for, this is common denominator, so they'll share the same denominator. We have root 4 minus root 2 all over, sorry, not root 4. root 6 minus root 2 all over 4. So this is your answer without making use of a calculator. So we go over to another example. Let's see. Question number 2 says you should look for. You should solve cos 75 degrees. You can express 75 in terms of the special angles. Now the idea is just to express it in terms of the special angle, because without using a calculator, there's no way you will know the answer to this. You understand? So we're going to have cos, and we can use the same 30 and 45, but this time around it's going to be plus. Now according to, okay, this is not going to serve as our A and this is going to serve as our B. Now you might ask, what if you rearrange it? If you rearrange it, you're still going to get the same answer. If you take 45 as A and 30 as B, you're going to get the same answer, because 30 plus 45 is the same thing as 45 plus 30. But mind you, 45 minus 30 is not the same thing as 30 minus 45. So when it comes to plus, you can rearrange it, but when it comes to minus, don't rearrange it. So the cos formula, the cosine formula says that, according to what we wrote earlier on, states for addition, states that cos A plus B is equal to cos A cos B minus sin A sin B. So we're going to apply the same principle here. So the formula says that cos A plus B is equal to cos A cos B minus sin A sin B. So we're just going to plug this in. That means cos 30 plus 45 is going to give us cos 30 cos 45 minus sin 30 sin 45. So cos 30 from our special angles, cos 30 degrees gives us root 3 over 2. Cos 45 gives us root 2 over 2. Sin 30 gives us 1 over 2. And sin 45 gives us root 2 over 2. If you're confused where we're getting this stuff from, we explained it here. Recall, this is what we mean when we're writing all this stuff. So we're going to solve this. Now root 3 times root 2 gives you root 6. 2 times 2 gives you 4 minus, this is root 2 over 4. Similar denominators, so we're going to have the same LCM. So we're just going to write root 6 minus root 2. Yeah, we've gotten the answer. So this is another example. Let's take one more example. Question number 3. Let's say we have tan 15 degrees. Now this can be expressed as okay, let's not use 45 and 30 again. Let's use tan, let's say tan 60 minus 45. These are all in degrees, please don't forget. So what does tan say for compound angles with difference of two compound angles? Okay, it says that we should find the difference, and okay, let's make use of the same formula. So it says that tan A minus B gives you tan A minus tan B all over 1 plus tan A tan B. This is what the compound angle says we should do. So our 60 becomes our A and 45 becomes B. That means tan 60 minus 45 is going to be tan 60 minus tan 45 all over 1 plus tan 60 tan 45. Now, tan 60 will obviously give us the square root of 3 special angles. Tan 45 is 1 over 1 plus tan 60 is root 3 times tan 45 is 1. So this is going to give us root 3 minus 1 over 1 plus root 3. Now we cannot leave our answer this way because we have to rationalize. When we go to solve, we have to solve this. What this means is that whenever I try to solve a fraction involving surd, they don't want to see square roots at the denominator. So you have to let go of this square root. So we're going to do something called rationalization. So we're going to first of all look for something called the conjugate. The conjugate is just, you look at the denominator, we have 1 plus root 3, right? Now the conjugate of this is going to be 1 minus root 3. So we're going to use this conjugate to multiply both the numerator and the denominator. So we're going to have, this is going to be root 3 minus 1 over 1 plus root 3. Now you multiply by the conjugate, so 1 minus root 3 over 1 minus root 3. So we're going to try to open this. Now we're going to have a bracket, root 3 minus 1, multiplying 1 minus root 3 all over 1 plus root 3, 1 minus root 3. So we're going to express this. Let's quickly erase this. Now we're going to try to open this. Okay, let's try to solve this before we go further. Now, so this is going to, what's going to happen is that the first term here is going to multiply this and also this. So root 3 times 1 gives you root 3. Root 3 times root 3 times negative root 3 is going to give you, now if it's just like you say root 3 times root 3. This is going to be square root of 3 times 3, which gives you the square root of 9, which gives you 3. So whenever you have the same roots multiplying each other, just pick the value in one of the roots. So root 3 times root 3 is going to give you negative 3. Now we're done with this first entity. Now the second entity is going to multiply this and also this. So don't forget to consider the sign. So negative 1 multiplied by 1 gives you negative 1. Negative 1 multiplied by negative root 3. Negative negative gives you positive. So positive root 3. Now we're done with the numerator. For the denominator, you can either express it the way we express the numerator, or we apply something called difference of two squares. Now the difference of two squares says that if you have an entity a squared minus b squared, it's going to give us a plus b, a minus b. So this can work interchangeably. If you have two brackets with the same entities with difference of just plus and minus, you're going to get back this. So applying this same principle here, this is a bracket, two brackets with the same entities, just plus and minus that differentiates them. So you're going to have 1 squared minus root 3 squared. If you express this bracket, like if you open it the way we opened the one at the numerator, you get the same value, but this is just shorter and faster. So we're going to be left with we have root 3 minus 1 plus root 3, right, over 1 squared minus root 3 squared. That's what we have here, yeah. So going back to this now, we're going to add and subtract like terms, and we're going to have root 3. This is going to come forward plus root 3 minus 3 minus 1 all over 1 squared gives you 1, root 3 squared gives you 3. So now this root 3 plus root 3 is just like you saying a plus a. A plus a gives you 2a. So root 3 plus root 3 is going to give you 2 root 3. Minus 3 minus 4 gives you minus 3 minus 1 gives you minus 4. Just like you're owing somebody 3,000 and you also go and borrow again, you borrow another 1,000, that's 4,000 in debt. So 1 minus 3 gives you negative 2. So you can't just stop here because you still have something to do. Now, just the same way we said, if you have a over 4 plus, okay, let me not use letters. Let's use actual numbers. Let's say you have 1 over 4 minus 2 over 4. Okay, that's nice, 2 over 4. Minus 3 over 4. Similar denominators, right? This is going to be 1 minus 3. Now, you can also reverse this. If you have two things adding or subtracting each other on the numerator, all of them will share the same denominator. So applying the same principle here, I'm going to spread this out to be 2 root 3 over minus 2 minus 4 over minus 2. Now 2 will go here, right? Now this minus will come up because plus divided by minus gives you minus. So negative root 3. Now 2 1 to reduce this to 2. Negative divided by negative gives you positive. Now the trick with this negative and positive symbols is this. When you have two signs, this is going to give you plus. It's going to give you plus. When we have these different signs, it's going to give you negative. So the idea is similar signs gives you positive, similar signs gives you positive, different signs gives you negative. Whether it's multiplication or division, it works the same way. At the numerator here, we had plus, although it was not written. Plus divided by minus gives you minus. Now at the numerator, we have minus, denominator minus. Similar signs gives you positive. So this is basically the answer to the question, tan 15 degrees. So this is a way we can get it without using a calculator. So we're going to take more examples on this, where we have to apply what we did earlier on, SOHCAHTOA and so on and so forth. So first example says that if sine A gives you 4 over 5 and cos B gives you 5 over 13, you should evaluate A. Okay. Evaluate sine A plus B if okay, for A, if A and B are acute. B, if A is obtuse and B is acute. So these are different examples from all the ones we've been solving before, like a combination of everything we've learned so far in this video. Now, consider in this case we have two reference angles. Therefore, we're going to have two right angle triangles. So the first right angle triangle, I have another one here. So let's assume this to be a right angle triangle. Now this first right angle triangle has a reference angle of A The second one has a reference angle of B. So for the first one, they said sine A gives you opposite over hypotenuse, right? That means your opposite is going to be your 4, your hypotenuse is 5. So according to our Pythagoras triple, we have 3, 4, and 5. So automatically this becomes 3. Now for your second triangle, which has a reference angle of B, this is adjacent. And this is hypotenuse. So your adjacent is the place that two angles are resting on. So this is 5. And your hypotenuse is 13. This is also a Pythagoras triple. 5, 12, and 13. So this is automatically 12. That means for this first triangle, cos A is going to be adjacent over hypotenuse, which gives us 3 over 5. And tan A is going to be opposite over adjacent, which gives us 4 over 3. This is for the first triangle. And for the second triangle, we already have cos, right? So sine B is going to be opposite over hypotenuse, which gives us 12 over 13. We already have cos, so tan B is going to be opposite over adjacent, which gives us 12 over 5. So the reason why we are 3 so here, the first one with A, we have sine, cos, and tan. That's the reason why we have the complete tricks in start the course of this question, just in case anyone. For cos for B as reference angle, we need to find the tricks. So we have cos, we now have sine and tan. This to sine and tan. So let me quickly write this out somewhere else. So it's important to sine A, according to the question, is 4 over 5, right? But when we solve, we got cos A to be 3 over 5, and we got tan A to be 4 over 3. This is where we got all these stuffs from this place. We solved for this, and the question gave us sine. So yeah. Now back to this again. We also know that cos B was given to us as, okay, let me write here. From the question, cos B was given to us as 5 over 13. And sine B will be, according to sine B as 12 over 13. We got our tan B as we got it as 12 over 5. Now we're going to see why we are doing this. Now the question says we should solve if both of them are accurate. So we should solve for sine A plus B. So according to our compound formula, sine A plus B says sine A cos B plus cos A sine B. So we're going to apply that principle here. So sine A plus B gives us sine A cos B plus cos A sine B. So from this our analogy here, sine A is 4 over 5, cos B is 5 over 13, cos A is 3 over 5, sine B is 12 over 13. So this is the reason why we have to look for that tricks. If you think for this question, we're not making use of tan. So tan is irrelevant here. But if question comes up, we need use of tan. Just go through this process. So let's try to finish this off. Now, by 4 gives us 20. 5 times 13 gives us 65 plus 2 times 12 gives us 36. 5 times 13 is 65. Similar denominators, 20 plus 36 over 65. This gives us 56 over 50 over 65. This is basically the solution to this for the A part. Now the A part says that if A and B are acute, so you don't need to consider anything. So this is your answer, 56 over 65. Now the question also says for B part, if A is obtuse and B is acute. So let's make use of this place to solve. Let me quickly erase this. Now, when A is acute, when A is obtuse and B is acute, now we go back to our tricks. Remember we said when an angle is obtuse, this is CAST. Obtuse like this concordance. It means that only sign is going to be positive. Every other sign is going to be negative. So since A is obtuse, it means our cos is going to have a negative sign. Both our cos and tan have a negative sign. So this is going to change to negative 3 over 5. This is going to change to negative over 3. So that's the only difference. But they say B is also acute. So nothing for that will be. So we're going to solve using the same process. Same guidance that says sine A plus B gives us sine A cos B plus cos A sine B. So this is sine A is going to be 4 over 5 as usual. Cos B remains the same, 5 over 13. Now cos A is going to be negative 3 over 5. Sine B is going to be 12 over 13. So 4 times 5 gives us 20. 5 times 13 gives us 65. Negative 3 times 12. Negative 3 times 12 gives us negative 36. 5 times 13 gives us 65. So similar denominators, 20 minus 36 over 65. 20 minus 36 gives us negative 16 over 65. Now, let me review, let me write this again. The first example says that both of them are acute, so we should normally understand. The second example says that A is obtuse. So in this thing we represented, remember what we said, that if you have a quadrant CAST, you have a quadrant this way, CAST. This quadrant is this way, so we're going to rest here. And when A rests here, everything here is negative. Let's set sign. That's why our sign is going to remain positive, our cos and negative sign. We didn't make use of tan, just in case the question requires you to make use of tan. That's why we have to change this. That's the only variation in the two questions. And you see that obviously we got different answers from our calculation. So this is basically what we're going to stop in this video. Thanks for watching.